We'll work on presenting in a couple weeks here, but when you do present, and because of schedules of classes that I might only be able to get whoever is available, there's only 2 of you that's available to come in at from 9:30, because I don't really want to mess up your, like you're available at 9:30 on Tuesday, Thursday. Are you available at 9:30 on Tuesday, between 9:30 and 10:45?
9:30 to 10:45? Yeah, I can get it.
Okay, because if I can do you 2, just because.
For what?
I feel, just to present, because remember how last year, the juniors last year presented to your methods class?
Yeah.
I'd like to have a couple people present to the methods class so they know what is coming up for them. However, because of some other things, I only have an hour and 15 minutes on Tuesday and Thursday instead of like 2.5 hours that we had for block 1. And so I don't have a lot of time.
Okay.
Yeah, I don't have a lot of time in there, so actually if I just have 2 people present, you 2 can just actually present it here, just with us 4, or you 4. Yeah, so we'll probably.
Yeah, because I have a class in 20 minutes.
Okay, so what I do is that when you present, it doesn't even have to be 100% complete when you present, as long as it's 80% complete.
Because even I remember they.
And then I'm not gonna look at them until the end of this semester. Okay, but the tendency is to forget it if you don't. So, but if you have just 1 hour to complete after your presentation, present it at your presentation. I usually say, okay, now you can go ahead and submit it into a document from Methods 1. So all 3, you guys all have Methods 1 at the same time, right?
Mm-hmm.
Yeah. Sometimes there's people from others. So you just go into your old Methods 1 class, and there's a document there that says TW Divine Portfolio. And you just
Sounds nice.
all right, did you learn more than you ever wanted to know about parallelism? What are my 3 axioms for teaching?
Know your crap.
Know your trap.
Know
more than your graph. And teach what though?
From the
overflow.
From the overflow, not teach the overflow of knowledge. Teach from the overflow of knowledge of graph. So, yes. So the crap we're talking about today is parallelism, right? I guess when I first think about this concept analysis, did you ever think about that question? Is a line parallel to itself? When you see that, like, where's your mind go? Does it just go home? What?
Well, I thought of this from 2 different points.
Okay.
The first is whether or not they were on the same plane, but say
Okay.
the same line would be say transposed onto another plane.
Mm-hmm. Okay.
So that way, if you look at it like this, you'd see 1 line, but there are 2. And then another one was literally, it's the same, it's not unique. I mean, they're both 1, so therefore they'd be unique, and it would still be only 1 line. So. Okay.
Well, all right. Well, so let's talk about that now. And I'm not sure about your first part, but hopefully you read a little bit when you started thinking about this. My mind immediately went when you said 2 planes. Could they be on 2 planes? If this is a plane and this is a plane, and you had a line here and a line here, it's a good question now to ask this, because now clearly this isn't the exact question, because they're not the same line because they're on different planes, okay? But in your reading and your studying about parallelism or parallel lines, if the line was this, if the line was here and the line was here, you'd say you might say they're parallel in some sense. Okay, let's just say that parallel in some sense. But if the line was going this way on this plane and this way on this plane, would they be parallel? Well, why do you say no?
Because I always think of...
In some sense. Let me clarify what I said. Would they be parallel in some sense? But go ahead, what are you going to say?
I was going to say, I always think of parallelism in the definition of all points are equidistant.
Okay. So
they're off to the side there. They're not the same.
Okay, so understand what he's saying there. When you think about 2 parallel lines, if I drew 2, what you'd think of would be parallel lines here, one way that I hope you saw when you were looking at definitions is something about a distance, right? So always the same, and from geometry, remember, when we say distance, we mean what kind of distance?
Straight line.
Yeah, so
Perpendicular.
perpendicular, right? Because you gotta watch it, and your students will catch you on that. Because straight line, well, that's a straight line. Yeah. I mean a straight line. I mean a perpendicular. Okay. So you have to learn that as teachers. That's why we want to learn how to be precise in our mathematical speaking. So anyway, but this distance there, this distance there, this distance is always the same. So understand what Cody is saying. If I initially go this way and this way, I might be able to get away with that. Okay? If I go this way and this way, then I guess then this point over here has no perpendicular to that, right? Has no perpendicular to it. So which point are you going to use? Well, yeah, but clearly, if this point here is perpendicular, right, then the rest of them aren't going to be. So that thought process leads me to this question then. I ran 5 miles yesterday. My distance was 5. I ran 12 miles one day. My distance was 12. I ran 0 miles one day. Well, is it possible to run -5 miles? No, my distance could never be -5. I ran 0 miles yesterday. Is 0 a distance? I mean, is 0 a distance? You went none, right? It's none, right? There's no distance there, but is it a distance? So now your question is 0 a distance? Because the two lines that are lying on top of each other, if that's my only understanding is distance between, then the question is 0 a distance? You know, and that's something that we have to think about. I'm not saying there might not be good arguments to say whether. So I don't know if I know 0 is a number, but -5 is a number as well. But in the realm of reality, we do consider 0 a distance in the sense that how far do I live from you? Okay, maybe for 50 miles. All right. How far do I live from my wife? 0 miles, right? Well, this far between our beds. Actually, it's a king bed, so that far, because I get this much space, and then she gets the rest. But anyway, so we do in reality usually think about 0 as well. Okay, so think about your other definitions, or think about. Oh, go ahead.
The thing with like 0 distance would be like, what is the distance from this pencil to itself, though? Like. Okay. That's another thing I thought about was
because it is itself.
It's the object, yeah.
Okay.
Like, yeah. So I don't consider the distance though when we talk about it though.
When you talk about with itself.
With itself, yeah.
Okay. All right. And again, we just have to make sense of this. Sometimes there aren't right or wrong answers. I think there probably is based on some of your definitions, because read me some of your definitions. Like, what did you? I wrote down 8 different definitions, and many of them are the same. So don't think that there are 8 actual different definitions. But like, just give me a couple. Give me one.
Lines in a plane which do not meet. That is 2 lines in a plane that do not intersect or touch each other at any point.
Okay, where'd you get that point, or where'd you get that definition?
That was online. I just
Googled it and said that. So what? Okay, is that kind of what you got?
Yeah, I have a similar one, but from Glencoe.
Yeah. Okay, so wait, read this whole thing again, because understand this. When you go to a math dictionary, it might give you like a typical dictionary, like 5 different things, but each one is its own precise definition, right? You don't know, and you usually get those from textbooks. And people would just copy these things anyway, from encyclopedias and dictionaries. But when like a random person just says, here's my definition of parallel, or when we're explaining it to a kid, we're probably not giving what we would consider a precise definition unless I write something up there and it's one sentence, right? If I just start rambling about it, remember definitions really just need to have the necessary and sufficient conditions, right? For it. But read again what you said, and I'm going to stop you at various times. Go ahead.
Lines.
Stop. Okay? Why did I say stop?
Well, what's his
Lines.
line?
Well, she said lines
Oh.
in plural, right? I stopped her abruptly, right? So I don't know if everybody caught that. Right? So the question is, when you say lines, and we got to be critical readers. Okay, we got to be critical readers. So when you say lines, what's the straight? But when I just say lines, the English implication there is more than one, because you didn't say a line. So I guess I could answer the student. Well, let's read what the definition says. It says lines that continue.
In
Stop.
a plane. Lines in a plane which do not meet.
Okay, and that was it, right? There was kind of a period there.
Yeah.
That do not meet. Okay, so lines in a place. So it's the implication is two, right there. So pick apart these definitions, folks. You know, you gotta definitions are there for a reason, and we don't just read them and say that's the definition, now memorize it. I mean, we pick them apart and say, what the heck does this mean? I mean, that's a meaty definition. It's lines, the implication is two, because the next sentence actually does say two. That's why I stopped you. Right? You do say two lines. So I wanted you to stop there because I could get out of that, lines, so there has to be more than one. The next thing she said was what?
Do not meet.
Before that even.
On the same
It
plane.
lines in a plane, right? It says in a plane. Now, that totally takes away if you're thinking about plane here, plane there. Because we have a special name for those who ran into it.
Oh, I did
It's a weird word, we don't use it. Well, I use it a little bit in statistics. When instead of the bell curve, it's what?
There was something about skew.
Skew, those are skew lines. This line, even though you might look at this line going this direction and this line, because somebody's definition had something about going in the same direction, I'll bet.
Yeah.
If you really look, right, going in the same direction. So I might be able to say this and this are going in the same direction, but they're not on the same plane. So hopefully it would say two lines in a plane. But I might be able to say going in the same direction, so I might be able to meet, and I might even be able to meet the distance thing, right? However, though, these two lines are not parallel, they're skew, because I could turn that plane, I'll just pretend I'm doing that, right? And that line's going this way, and that line's going that way. They still don't touch, but they're in different planes. We have a special name for those. Those are skew. So when I look at that wall, I say that corner, or that side there, that edge, and I know it's not very good, right? Because it's got that little thing, let's pretend. Pretend like that, and then that back wall over there. Now those are all on that wall. They're parallel. Clearly, that wall and up there at that ceiling that's on the wall, right? Those intersect, not parallel. But you gotta be careful because that line there, okay, and this line here, I just do that. Should have chosen a better one, but I'm doing it. Somebody take a picture. Oh, there it is. But those lines there. Oh, now I forget it. But anyway, you get it. Those lines there don't intersect, right? But they are not. We would not consider them parallel. Okay. Then you got the distance thing going in there, right? So, and wait, keep going. I said do not touch, right?
I do not meet you.
So right there, even though the implication already is lines, what would we say about like the same line? Even if you could break it, well, even if you wanted to say they are actually two lines, they're just lying on top of each other, okay? Because we do that in algebra, right? We say, you graph that line, and instead of graphing another one intersection, we say graph the second line, and we put it on there. We say they coincide. Because it's too cold outside. That's a good one. I know Brian's going to use that one. But what's that? Not that one. But they coincide, and we call it two lines, but they're really not two lines. I mean, it's really just the same line. But we say it's two lines, right? We say it's two lines. So you could say that they intersect everywhere. So but we do end up saying there's an infinite number of common points, right? And I don't know why we necessarily say there are two lines, because it is really just one line, and that. But well, anyway, yeah. Give me another definition. What do you got, Ryan?
I'll use my Google definition.
Okay.
Side by side having the same distance continuously between, which we sort of already went over.
But I like the wording, right? You know, side by side. I wonder, does side by side imply they're in the same plane?
I determined from this Google definition, I think there is a huge implication of the Euclidean parallel postulate along with it. So,
I mean, I like the distance. So, my only question with side by side is, would you consider this? Like, so for instance, if I had this, I'm gonna call this a plane, and then this a plane, and clearly if I have two lines here, we'd say they're side by side. Okay. Now, would I consider this and this side by side? Well, if they're the same distance apart, I would say yes. Now we have to make sure we understand plane. This plane doesn't actually stop here, right? And, this is my conception of plane, but a plane, this is just my representation of a plane, but just like a line has no thickness, right? So you don't actually see a line. There are lines everywhere in this room. You don't see a line. You represent a line on the chalkboard, but there is no line. So, I mean, there's lines, but you don't see it. That's weird. But you don't see the wind either. You see the effects of the wind. So, but my point is, same thing with the plane. This plane goes forever. So this plane here, if this is really beside it, is that same plane. Now, if I drop this, now is it beside though? And not right beside each other. So it might depend on what your definition of beside is, right? It's to the side, but it's not beside. I don't know what's your definitions and terms really do matter. But you got the whole distance thing. So again, you still have to argue, well, is 0 a distance? But don't forget about the lines part. Okay. Give me one you have.
Well, Ryan's side by side, I found like the origin of the word was Greek.
Oh yeah, okay.
And then it was parallelios, and that meant side by side.
Okay.
And then they broke it down, and they broke it into pair, which means equivalent to, and then alios, which meant one on another. Like one on other. Wait, no, one another. Sorry.
One another. Yeah, one another. Right.
One another.
Yeah, I don't know why. I don't think I have.
And that came from dictionary.com.
Yeah.
And then also it had like a definition with it also.
So parallel. So the origin of the word beside each other, right? So you understand?
Yeah,
side by side. Yeah, side by side. Yeah. Okay. Yeah, that's good. I like that. Yeah. See, that's good. You just learned a little history too.
Mm-hmm.
Cool. Okay. Anything else about definition? Anything you find interesting with your definitions?
Well, mine said that it never converges or diverges. That's what dictionary.
Never converge or diverge. So, it's got the distance thing. It's an interesting way of thinking about it or describing it, right? Never converge or diverge. What about, anybody come with a little bit more of an algebraic? Because how many people looked in geometry books?
I did.
Did you look at an algebra book for definitions of? I see you didn't do that. I did. I even looked in calculus books and pre-calculus books and stuff like that because I'm smarter than you. But if you look at an algebra book, listen to the definition. Right, where is it? Lines are parallel if their slopes are the same.
Oh yeah, I did.
Right? Because geometry, you don't talk about that. Right? Geometry, you don't talk about slopes. Now, that part of algebra, and understand this from history of math even, that part of algebra though is, and we study it in algebra, we put it on that coordinate plane, right? But that is the intersection of algebra and geometry, analytical geometry, right? The geometry we studied last semester in geometry class was synthetic geometry, right? Because you're just really looking at the figure itself. We don't put it on a plane. But once you do something like this, once you say, now, and what if I actually put this parallelogram someplace up here on a plane? I don't want to put parallel. I say there are 4 points. And now I say, let's prove that this is a parallelogram.
Fun.
I've got a whole other way I can prove it, right? I got a whole other way I can prove it because I can actually say I can actually show that the slopes are, right? Now, without mentioning slopes, I prove something is parallel by showing that maybe angles, right? Some of those special angles. Maybe I have a definition of a parallelogram that if opposite sides are congruent, then they're parallel. Again, how do I do that? But I usually do that through corresponding angles, alternate interior angles, something like that. I have to know some more information about it, obviously. But on the coordinate plane, if this, you give me a point here, 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 and to prove that it's a parallelogram from an analytical geometry standpoint, I'm just going to find slopes. If they're equal, parallel. If they're equal, parallel. Because we all know the questions that, write the equation of a line, right? That's half of algebra 1. Write the equation of a line that's parallel to this line that's given and goes through a certain point, and what do you have to know? You got to figure out the slope. So that's an interesting way of looking at it. Oh, but actually, here's an algebra textbook here because, and let's make sure we understand why this definition is written like this. So the one just told me lines are parallel if their slopes are the same. That actually did not come from an algebra book. That actually came just from a dictionary, like one of my math dictionaries. But an actual algebra text said this: two distinct lines. So I appreciate when they say two distinct lines because they make it a point to say two distinct, even though you can certainly say, well, it says lines, so the implication is, but as soon as you say two distinct, right, then you're clarifying that lines. Because just saying lines and saying everybody has to understand that line, there is an assumption there, that you're understanding plural. But two distinct lines are parallel if their slopes are equal, but listen to what the algebra text also said, because it knows where it's going in its problems. It says if the slopes are equal or both are undefined. That allows you, right, to have vertical lines that are parallel because,
well, that's the same slope.
Well, except for the fact that this,
It's not a numerical.
it's not a number, right? Yeah, because remember this, and I like to ask students, especially like people who are going to be teachers, when is it in mathematics that 0 does not equal none? Because usually we think of if you have 0, you have none, right? But when you're talking about slopes, 0 slope is a horizontal line. No slope, or it has none, or it has no slope. No slope is that.
It's like the difference between 0 and an empty set.
Right.
Yeah.
Right, exactly. Yeah, the difference between that thing and the set that has 0 in it, right? So you have to be careful with that, and you really have to, when you're teaching then, from a pedagogical standpoint, right? So it's because everything comes back to pedagogy. Part of the pedagogical part is of what we're discussing right now is definitions are important. Why we call things certain things, why we define them certain ways. It all means something, distance stuff, whatever. But if you don't clarify, and I'm sure there are teachers out there that would accept no slope for that, because they would say, well, I want them to write undefined, which is fine, but this is also not correct for a horizontal line, saying no slope. There is a slope, and that slope is 0, okay? It doesn't slope at all. Well, in the real sense, right? You can say, well, that's a flat road. It doesn't have any slope to it. You could say that, but that's not what we say mathematically. We say it has a slope because you can calculate it, and the slope is 0. This is no slope or undefined. So that's why the clarification would be there, because some smart aleck kid's going to say, well, these are undefined and those aren't numbers, so how do I know those are equal? One of my oldest textbooks, I looked up a 1918 book, and it said, lines in the same plane, everywhere the same distance apart. I just like reading like old stuff. We would never read that in a modern textbook. Everywhere the same distance. You'd say there they're equal distant, or everywhere the same, but it does make sure lines in the same line. So. All right, some applications. What did you find? Where are some applications of parallel lines? Where are they used in mathematics classrooms and outside? Now, usually it's easy for us to talk about inside mathematics. Where do we use them? Sometimes it's a little harder to think about, parallel line because it is just a concept. It's not a procedure. It's not a It's not like a problem to be solved, right? It's just a word. It's just a concept. So it's not like there's a problem out there that asks for something with parallel lines. But where else could it be used? So where else? Inside math, outside math. What'd you find? Anybody just starts out. What'd you find?
The one I like to say is data tables.
Okay, what do you mean?
Well, data in good organization of data, you want completely parallel lines.
Oh, okay.
You if they're intersecting, the data's going to look all extremely unappealing to the eyes.
Right. Well, and actually, that's a good point. I've never thought about that, but I work with my son's fifth grade class a lot, and so nobody can keep in parallel lines there. Okay.
I mean, yeah, if you can draw, that's another story.
The ones who are well, but that's funny you said that because they were working with. Not quite yet the long division algorithm, but it's the division algorithm. But they do it. They first start out in what's just called partial quotients strategy. So basically, it looks like this. Because some of the chocolate's good. They do this. They do this, and they take this straight down here. Okay, and so if they're taking 4. And you're dividing that into 3,846, something like that. It's a great strategy. It makes a whole lot of sense. Rather than saying 4 goes into 3, no, 4 goes into 38. If you think about it, that is the long division algorithm is an extremely difficult procedure for kids to get in 5th and 6th grade. You just say this. Because all you're doing is taking out a bunch of 4s. How many 4s do I want to start with? And the good thing is, you can start wherever you want. Okay. Hopefully you don't start with 1 right now. All right. But most kids will do something like, I might say 100. Can I take out 100? Well, I'm sorry, 1,000. Can I take out 1,000? Well, no, because that's 4,000. Right. Now you want them eventually to get to seeing this, 3,846. They're really doing 4 into 38. So you see what I'm saying, right? It's 9. So 900. But who cares first? 100. Okay? I can take out 100 and then 100 times 4, 400. All right? And then, you lower that. And then the answer is down here, adding them all up. I don't want to get into all that. The point is, though, talking to my students about keeping things in parallel lines, right? That's important. And what they give you in some of their workbooks and that is they give a grid for them to work with, right? And they put a 4 in there and that. So that's actually really good. Parallel lines are important because
anyone with OCD would agree.
Right, exactly. And you can tell, and at 5th grade, most of the kids who do a really good job are the ones that keep everything in line, and the other ones are struggling right now.
I would be a struggling student.
But what do we do? They're important because when you're adding decimals, you got to keep the decimals. Okay, and you want to keep this here, so you make sure you're caught. That's a good place. Good place. Yeah. Where else?
I have one outside of
okay. What is
classroom. Lines on a paved road.
Lines on a paved road, right? You got to keep them. You got to keep them parallel, right? I mean, I don't know how those people actually drive and paint. You ever see them doing that? I mean, I know the thing is putting both of them through, but they still have to drive straight.
Yeah.
And you can tell sometimes when they don't. It goes a little weird. And when they run over it with their vehicle, right? It goes there. But yeah, that's good. Okay. What else?
Like with pillars and stuff, like architecture.
Construction, architecture. Okay, right? You gotta keep things parallel, keep them the same distance, apart. So when I was working construction before I went back to college, I did
everything.
I wasn't very good at it. I sucked as a carpenter. So what we would have to do is, that's probably why I got fired. No, I didn't get fired. But if I was building a wall, I'd have the bottom plate and the top plate, okay, and then 2x4s in the middle, right? Well, we'd at first throw in as many as we thought was going to be there, right? I mean, the plans would tell us how many, of course. But you throw that there. But you had to take this this board here, the 2x4 here, and start measuring off here 16 inches on center, right? 16 inches on center. And so 16, 32, 48, and all that. Well, you got to go to the next board over here, the top board, the header board, and you got to go there. Make sure you start here and not there, right? Because it doesn't necessarily end evenly. So that's why you want to do that. And you start here and go 16. So they need to be parallel. The homeowner's going to get pissed if he's hanging something, right? And the stud finder says, well, stud finder, which never work. The stud finder says the board is here, and they go straight up, and you, right, it was angled a little too far away, and he misses. You know, he's straight up from where that stud went in, or that nail went in the stud, and up here, well, crap. You know, that, so that's good. You got construction, got to make sure things are parallel. Where else? Some typical math stuff.
Well, in that, like you said, with parallelograms and stuff.
So parallel lines, right? Parallel lines cut by transversals. You know, parallel. You know, that's some. And like the proofs in there. Just anything with polygons, I guess, right? No, outside, yeah, some like flight paths. Okay, you know, think about flight paths. Maybe you're flying in a formation, the Blue Angel, something like that, right? You know, they want to keep their bearing the exact same, right? Like how do they know they're going? Think about it. How do they know they're going parallel with each other and making that perfect, you know, formation, right? Well, I can guarantee they're not like looking down and doing that, right? You know what happens when you're riding a bicycle, right? You look like this and you drive that way. But they're certainly not doing that, right? They're just paying attention to their instruments. They know exactly what they're doing. They're certainly not like looking at that tree and go right because they're in the sky. So they're not looking at a tree and saying go straight for that. How are they keeping so parallel? I mean, you know, they're looking at their bearings. They're going parallel. Optics uses a lot of parallelograms or parallel lines. Think about a periscope even. Okay, periscope, right? You look through here, and you see up there, right? So what's it do? You look through here, and then there's a bar there, and there's that. These two things are parallel, right?
I'm always amazed how that worked as a kid.
Yeah, well, there's a mirror. There's a little mirror there at 45-degree angle. So you look through here,
has to be.
And I suppose if the mirrors were created correctly but differently, the top and the bottom wouldn't have to be parallel, right? You know, I guess you could. It's parallel because it goes 45, right, and it looks up and hits it at 45.
Yeah.
But could you make this one something and that one something
Well,
else?
60.
Yeah, you could.
Yeah, and then
But then like
but you wouldn't be looking
the
straight
line
at
of
it.
sight would be a weird.
Yeah.
So you wouldn't be looking
Doesn't the
straight.
periscope also have like a little tube before you're looking at? So could it possibly like interfere with like looking at part of the wall?
And depending, you know, I'm thinking of a very simplistic one that you could just make with PVC pipe. Right? You can make your own PVC pipe, and then, you know, somehow glue a mirror, you know, in there. It's probably a good activity for kids. I do that with my kids.
I want to do that now.
I know, not so do I.
He's gonna make his own submarine.
My youngest is now after me to make a dog food dispenser. He saw it on a stupid YouTube channel. My 5-year-old, no, 6-year-old, I guess he is now. But it's just, you make it out of cardboard and PVC pipe, and then rather than, you know, of course, the video says, who wants to do this? You grab the dog food and you spill it, right? You know, all over the place. And so you put it in a container that screws on top of this. You just make it out of cardboard, and it's a little lever. And you put the bowl down, lever goes in. It's actually pretty cool.
How did you spend cereal at that?
Well, that's actually pretty much the same. You screw those things usually and you have to.
One screw, not enough. 2, it's way too many.
Anybody find out anything else?
I liked what you said earlier.
What we said with construction, I thought of sewer lines, pipes.
Oh, yeah.
Underground.
Yeah.
Usually a lot of parallels.
Yeah.
Because of the way we make streets.
Okay, yeah, that's right, yeah. Because you gotta go parallel to that. I mean, kind of like that. It's probably not considered the exact same thing, but just surveying.
Yeah.
You know, surveying in general, right? You know, you see the guys out there with the transits or whatever, you know, they're using parallel lines. And,
Ooh, I just thought of another really good one. Railroad tracks.
yeah, and railroad tracks, right? You know, you gotta,
Yeah. Like 2 different.
Yeah.
That is extremely precise.
I know, I just got to thinking about that though. Why, or not why, how, I wonder how when you're building railroad tracks, though, how do you keep them exactly?
Is that why there were the boards? Perhaps,
Yeah, well,
at earlier times?
certainly the railroad ties, but I mean, still, you're measuring, of course, right? You
Yeah.
measure between them, but man, it's gotta be precise.
Around a turn.
Yeah,
Right?
no doubt.
Yeah, that's gotta be.
I'm sure there is some room for error because the wheels are kind
Yeah,
of.
right.
Yeah.
I mean, no more than
A couple inches.
Yeah, you can't do
Yeah.
that. One thing you ought to look up, wouldn't do it in here now, but there's a way of producing pi called Buffon's needle. Okay, that you put parallel lines down, and then I think the stick or straw that you cut out has to be so you could put whatever 5 parallel lines down, and then you get a stick or a straw that is the width of the distance between. So the width between the parallels have to be the same. It's not the year like that. And then when you and I didn't look up how to do it, but and then so if this is the pencil, you then just stand here and you drop it. Okay, you drop the pencil from whatever, and if you take the probability that the pencil crosses one of the parallel lines versus doesn't touch it, okay, if it lands like this versus like that, you can produce pi, to it. So it ends up being the probability of doing it. So it's Buffon's needle. So that's pretty cool. I haven't done it in a long time, so I don't know well. Some deeper questions: are parallel streets really parallel? If they're extended, do they eventually meet at the North Pole? What do you think about that?
We talked about this pretty extensively.
Oh, yeah?
We had some talking.
They can be parallel.
Okay.
Which one do they have now? Latitude?
Latitude.
Yeah,
was
Latitude.
Yeah.
Those ones not parallel. Like if they go directly up towards the North Pole,
Yeah,
right.
South
those are
Pole, not at all.
Those are
Or
longitude lines.
Latitude lines, or for that matter, any like.
Yeah, because longitude are
angle.
longer.
Yeah,
These are all the same, right? They're all great circles. What's that?
Lat's fat.
And lat's fat. Is that what it is? That's funny. Lat is fat. That's a good way of doing it. Because latitude lines.
One of them's the equator.
Yeah. Equator and then other. Yeah. But so.
We were talking. Then we got to talking about latitude lines, and even if they're not exactly latitude lines, as long as there's some like the angle is the same, they could be parallel.
Could just be parallel.
Yeah.
Yeah, but what I was arguing about for so long was it never like restricts the parallel to like say the great circle, whereas a great circle, if the two lines ended up creating great circles, then they're not parallel.
Right.
And then the reverse
So, but
is latitude lines.
based off that, we couldn't determine that the streets would create great circles or not. So
Right.
it created that whole.
And that's one of those questions that, really the answer is, who cares? But it's certainly an interesting thought question, right? The thing, I mean, it doesn't matter, that's never going to matter, other than the question of, hey, you call these parallel streets, right?
I'm gonna make
Two
an
streets
ultra
around the world.
highway.
Yeah.
Ultra highway. Goes the
Interstate
whole
1
way
and 2.
around.
Intercontinent.
But you say, it would have to be Interstate L1 and L2, right? But no, but it's just, it's a
continent. States.
But it's just interesting to have that little thought exercise that says, well, we call them parallel streets, but really because you're only looking at a plane there. Can lines that are not in the same plane be parallel? We already discussed that. Skew. That's the skew thing, right? And then we always talk about lines being parallel, but can planes be parallel? Well, I mean, just extend your definition, I guess, right? Two planes can be parallel.
Yeah.
But how do you define them? Well, you can't say.
I like the equidistant thing.
Yeah, right. Because you can't then say two planes are parallel if they're in the same plane and.
Yeah.
That makes sense.
The same
Right.
R4.
So the definition has to be somewhat revamped. So now we just use the distance, right?
Well, from the one math dictionary I looked up, it said lines and planes that do not intersect. So it did talk about both lines.
Yeah. Okay. Well, yeah, and then and some like, again, I'm not saying that you're always going to find this distinction because in working in Euclidean or in plane geometry, we do need to distinguish between that line and that line not being parallel, calling it skew. But in the real world.
It makes sense for planes though, that they could just say not touching, because if there's any like sort of
Right, then they're gonna touch.
then they would
Yeah,
eventually.
right, exactly.
That's interesting.
Yeah. Well, but then that brings up another point. If they're not plane, or if they're not parallel, then when they intersect, how do they intersect? In a what?
And technically it would be a line.
Yeah, two planes intersect and they form a line, right? They form a line, which is your visual for when we solve systems of equations. It's two lines intersecting in a point or not, but two planes when they intersect. So when you have 3x3s, right? The two planes or three planes could intersect in a line. 3 planes could be parallel, or 3 planes could actually intersect in a point. If this one's like this and the other one comes down like that, the only intersection would be a point. But that's consistent with your linear algebra, right? Sometimes you get one solution when you have a 3x3. That's a point. Sometimes you get that one parameter.
Wasn't that whenever x, y, and z were all 0?
Well, that's not homogeneous. Well, yeah, is that what's called?
Yeah.
That's the trivial solution, though.
It
Trivial
was-
solution to
yeah.
a homogeneous.
If you have if you have 3
It's 0,
vectors
0, 0.
in the what's it called, the basis,
Yeah.
and you could if you could boil it down to 1,
Yeah.
then there's
Then there's one.
But I thought
and
it would be
I forget.
a
It's been a while since I've
point,
taught
I
that,
think,
so I don't
or something
remember.
like that.
Yeah,
That's all.
the all zero.
I assume that if x had to equal y had to equal z had to equal 0, that'd be the one solution. If you could create another one, then it wouldn't be linearly dependent. That's what I was going for.
Yeah, it's been a while since I've looked at that.
Yeah.
But anyway, the point there is, yes, they could. And then what about, can a line be parallel to a plane? Well, a line. If you have a line parallel, if your definition is just going to be doesn't touch or same distance, then yeah. But what?
Well, the way I thought of it was with the same distance thing, it can be parallel to a line on that plane, but not to the entire plane itself. Because say you have, like, this is your plane,
Gotcha.
and then you have like this point over here and this point over here, these are not the same distance
Right.
because of that angle.
So if we're going to say that a line can be parallel to a plane, then we just can't use the okay, but yes, we could still say distance, because distance is always defined as a perpendicular distance.
Yeah.
So if this line is parallel to that,
Then the
it
distance.
is from here to there. It's not from here to there. We call that the normal, or the norm.
Yeah, the normal
The normal.
vector.
Yeah, the normal vector. Been a while since I looked at all this stuff, so it's not right here on the top of my head.
Count 4.
But what's that?
Count
Yeah,
four.
count 4.
Introduction.
But then, yeah. So that would be. But in essence, what you're saying is,
You're saying number 2 then, right?
you're
2
saying it
lines.
is a line.
Yeah, you're just.
Well,
Yeah.
you're saying that it is a line, but the line you're saying that it's parallel to a line, but keep in mind that is when you can say that it's parallel to another line that's not on the plane.
Yeah.
It's the
They're
plane,
not
right?
coplanar.
Right. They're not coplanar. So, but it's still when you say it's parallel to this plane, you are actually saying that that it is parallel. Well, if you're using the distance thing, but if you're just using the doesn't touch,
Doesn't
then it
touch.
doesn't matter.
Yeah.
So it is, parallel to that. So again, it depends on what your definitions
Yeah.
are important. Can two segments of a curve be parallel? If so, how does this change your perception of parallel? So actually, that kind of goes to the generalization. Can curves other than straight lines be parallel? Just curves that don't intersect, right? So the thinking, the visual, that I look at, I guess, is you have a parabola here, and then you have a parabola here. Well, these don't touch, and you probably would be able to say here though that these would all be, if I did my perpendicular distances, whatever. I mean, it looks like the way I've drawn it, they're all the same.
Yeah. You did like a circle, 2 circles.
Yeah, do some circles there. But what about? Is it possible? Well, okay. How about this then? Ever going to touch?
No.
Do we consider them parallel? Well, I mean, but it depends on what you're going to say parallel. If I'm going to define it as 2 curves on the same plane that do not intersect, yes, these are parallel to each other. That's parallel to each other. you know, when I ask these questions like this, one of the reasons that I ask these things are because I want you to, well, actually, do I say that down here? Yeah, look on the notes. I'm probably not going to go any further with this here, but notes on the concept analysis. Number one, the results of a concept analysis often make us realize that mathematics is not as rigid as it is sometimes made out to be, and it may suggest changes in our formalization and interpretation of the idea. So, you know, as a teacher, from a pedagogical standpoint, you have to be careful about coming across to your students, and I know this is not necessarily what you've taken away from your years of experience, but trust me, I think it helps you be a good teacher and reach more students, is we have to get out of saying, you know, this is the way it is, you know, this is the definition, and you have to use that. And I get that that's why many and probably most teachers teach it, because they want you to solve problem number 13 in your textbook, right? And to solve problem number 13 in your textbook, you have to use the strategy that I'm saying, the definition that I'm saying, and you can't, you know, veer off that. Well, you know, that's probably not much of problem solving. It's just exercise doing, which there's merit in that. I'm not saying that at all. But I'm saying that I'm saying that we can have certainly more pedagogical fun with mathematics and teaching mathematics if we don't come across always like you have to memorize this definition and do it my way and if you're going to get it, and allow for, you know, the creativity and the challenges that can come up with asking some of the hard questions, instead of, you know, well, we're not going to think about that right now, or I don't want you to think about it, I just want you to do what you know, the way I'm saying. Now, when it comes to the test, when it comes to PSSA, you know, play the game. You know, I'm prepping with the 5th graders in Belfont, Mary Walker, where my son goes for PSSAs now. Okay, you know, we're gonna, and you know, I mean, all year long they've been using algorithms and things like that, right? And they're allowed to use a calculator for part of it, okay? And the student, if some of the students are not on the practice exams using the calculator because all year long they've been doing things, you know, by hand, right? And the teacher and I are like, you have a calculator, use it, you know, check, make sure you know how to use it, of course, right? But the goal is to answer the question correctly, you know, A, B, C, whatever. It's not to show your work. You don't have to show your work in any with a free response, things like that. So yes, maybe I need to tell my students, okay, this problem, and this is why good directions on a test or an assignment are very important, because I tell my students, I want you to do this, you know, maybe, I don't want to say my method, but the way we did in class, or I want you to interpret such and such the way we interpreted it in class. You know, I think was I saying this class about the sharing in here? No, I guess I have a problem with always interpreting these kinds of questions when I say that I am going to share some money I have. I'm going to share some money I have with my 4 friends. You call me friends. Count yourself up. I'm going to share my money that I have with you, or that I have with my 4 friends. Well, in a word problem in elementary school, that actually means you're going to split that 5 ways. Yourself and that. Okay? As an adult, and especially maybe as a teacher, I don't know, I don't actually always think that just because I say share, and I looked up the definition of share, and there isn't necessarily anything that implies that it's my, well, yeah, equal amount, but let's even say I'm going to share equally. What I mean is, if it's just you and I can't give you everything and call it sharing. Yeah. But if it's me and 4 people, I can give it to just the 4 people and share. As a teacher, I share papers with you all the time, right? Yeah, I share papers with you all the time. And maybe I'm just a really nice guy and I don't necessarily care that I get my cut. Yeah. All right? But I think, what if I just shared it among my 4 friends equally? You know, the English word share has no implication that I can find that it means that I'm included. All right? But from a mathematical standpoint, when we're solving problems, you have to if you're going to get letter B, for it, or the answer in the back of the book. It's not going to work if you don't. So I have to interpret it that way.
The worst would be if they give you a 4 and a 5 both, and then they'd have different.
Exactly. I mean, so what's the better interpreter, or what's the better way to say? If I'm writing a problem, I would probably say, you're going to share it with you and your 4 friends.
Yeah.
Okay, but just to share with 4 friends. I don't think there's an implication there is, but I'm sure every math book that would have a problem like that would say that. And certainly every standardized test, I think it's very
Sure, they would say something like, this person gives some to them and then keeps, like they'd specify.
Yeah, something like that. So like, I guess what's the other word then? Would I just say that I give 4 people?
That's what I would say.
But what? But
Because
why is it sharing and giving?
Sharing does seem like it implies like you
Yeah,
give
sharing
as
with
well.
sharing with 2 people, I get it.
Yeah.
Well, anyway, and the last thing there is many times our students will challenge our understanding of a concept by asking us a simple question. And I can't believe how many times it's led to hours and hours of frustration and study when somebody asks a silly, stupid question I've never been asked, like, is the line parallel to itself? Don't disregard or avoid the questions, rather use them as opportunities to help our students and us understand the concept deeply. To help our students. That's what I have to fix for next year. So for homework then, just the next problem. So just to kind of show you a difference between a concept analysis and a problem analysis. So this problem, it's average speed problem. Now, if you read 1 and 2, you're going to see that there is a subtle difference. And this is an interesting problem because number 1 and number 2, and I don't think I want to show, well, I'll just say this. One of them is really easy and one of them is harder. Okay? But yet, from a reading level standpoint, look how close they are from in a reading level, same reading level, but also in the words. Number 1, if you travel for 45 minutes at 60 miles an hour, and then for another 45 minutes at 40 miles an hour, what's your average speed? Flip over to 2. If you travel to a certain place at a rate of 60 miles an hour, and then back at 40 miles an hour, what's your average speed? I mean, there's a subtle difference there, right?
Time.
One of them's hard, one of them's easy.
Yeah.
See if you can make heads or tails out of those 2 problems, and then we'll kind of pick that apart and call that our problem analysis, which we don't really look at problem analysis until next year. All right. Have a good rest of the meeting.
We just do these 2 problems.
Yeah, just that. Yeah.
Steve, I feel like you have some grudge against this kid who asked you, is a line parallel?
Yeah, exactly. I don't even remember who it was. I failed him.
Every time you say it, there's just a slight
Yeah.
angry tone.